Okay, now we're going to do Unit 1.3, which is analyzing limits analytically. The first thing, let's just look at what the graph of f of x is equal to a constant. And in this case, f of x is equal to pi. Now, it doesn't matter where my c is, all right? The value of the function is always going to be the same. So the limit as x goes to any arbitrary constant is, in this case, just going to be pi because that's the value of my function. My function's a constant. Now here is y is equal to x. You see it doesn't matter where my c is. All right, in this case, and let's just get on over here, oops. The limit as x goes to any value c of my function is just going to be that c value. If I come over to 6, it'll be 6 if I can draw a line straight. And this is kind of common sense. It doesn't matter whether you come from the right or the left. This is a very constant, or this is an easy to evaluate function. Now what if we have y to a power y squared, y cubed, y to the fourth, etc. Then this is y squared. You can tell by the color here. All right, red is y squared. The limit as x approaches y squared is 4, or what is that? 2 squared. What is it when it approaches 3 squared? Well, it's going to be 9. What is the limit when I'm dealing with y is x to the fourth? Well, that's going to be 2 to the fourth. And when I'm looking at y is equal to x to the fifth, then it's going to be 2 to the fifth. And these have an interesting theorem that just says the limit as x approaches c of b is equal to b. So basically this is my constant function. This is my f of x is equal to pi function. The limit as x approaches c of x is equal to that constant. This is my y is equal to x function. And then the limit as x approaches c of x to the n is c to the n. This is my y equals x squared, x cubed, etc. Functions. These are very, very straightforward to evaluate. They're continuous. So pause the video and do these 3 notebook problems. Now here are some properties of limits you need to know and you need to memorize them. If I take any constant, b, and multiply it by a function, if the limit as x approaches c of f of x is L, then the limit as x approaches c of that any constant times f of x is going to be that constant. Basically, you can factor the constant out. Similarly, if you add 2 functions, f of x and g of x, and f of x has a limit of L and g of x has a limit of k as x goes to c, then the limit of the sum is the sum of the limits. Also, the product rule says that if you multiply the 2 functions together and then take the limit, then the result will be the product of the limits. Now this will make your life so much easier later on when you can evaluate the functions separately and just multiply them together. The quotient rule, very similar to the product rule, as long as g of c is not 0, all right, then the quotient, the limit of the quotients is the quotient of the limits. And the power rule says that as x approaches c of any f of x to the n is equal to that limit to the nth power. Now, suppose I have a function at its x squared, let me move this a little bit, x squared minus x minus 2. How would I find the limit? Well, the first thing I can use Rule 2 to separate these, and you don't have to show every step after this unit. Okay, during this unit you do. All right, I can distribute this minus the limit as x goes to 2 of 2. So you take and distribute the limit across to each term, and now we can evaluate these. What is kind of hidden here is I can factor out this -1, because here my b is -1. So this is going to be -1 times the limit as x goes to 2 of x squared, plus, let's go and evaluate this. The limit as x goes to 2 of x is just 2. And then the limit as x goes to 2 of 2 is just 2. Okay, so those are going to cancel. So this becomes -1 times 2 squared, because I'm able to apply my power rule, or -4. Your turn. Pause the tape. Now, the limits of polynomials and rational functions are one step beyond what we just did. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is just p evaluated at c. You shouldn't have any singularities on polynomial functions. Now, as long as q of c is not 0, and that's a big caveat, you have to remember to put that in there, then the limit as x approaches c of r of x is equal to r of c, where r is defined to be the ratio of p of x divided by q of x. So you see why it's essential that q of c not equal 0. If it does, then the whole thing blows up in your face. So let's look at this limit right here. Let's let p of x equal x squared plus 1. Then the limit as x goes to -1 of p of x is -1 squared plus 1, or 0. And the limit, you have to do them both, even though it looks like it's going to be 0, because you'll see why in a minute, of q of x. Now in this case, I should put in here, q of x is just x. This is the limit as x goes to -1 of x, or just -1. So r of x is p of x over q of x. I know. You have to write it. So the limit as x goes to -1 of r of x is the limit as, well, it's just p at c divided by q of c, which is 0 over -1, or 0. Now, I always show a lot of steps. I expect you to do the same, particularly in the beginning. Now, theorem 1.4 involves a radical. The limit as x approaches c of the nth root of x is the nth root of c. This is actually a corollary of the power rule, because you know the nth root of x is the same thing as x to the 1 over n. Right? Your turn. Pause. Now, composite functions are a tremendous amount of fun, and they're also a pain. Okay, find the limit of how do you find the limit of a composite function? Well, suppose the limit of g is L and the limit of f is f of L. Then the limit as x goes to c of f of g of x is equal to f of the limit of as x goes to c of g of x, which is f of L. Let me kind of explain this. Let's just do an example. I think I'm better at explaining. You always work from the inside. So let's start right here. If f is x squared plus 2 and g is the square root of x plus 7, and I'm looking for the limit as x goes to 0 of g of f of x, you always kind of have to look at what happens on the inside. You see we've switched the g's and the f's, okay? So don't let that confuse you. You always look at what's on the inside. Take the limit of what's inside first. So I want the limit as x goes to 0 of f of x. And this is the limit as x goes to 0. And f of x is x squared plus 2. So it's 2. All right. Now, let's look at g of x. G of f of x is, now what is g? It's a square root. Now, I'm applying the outer function to this limit. 2 plus 7, square root of 9, or 3. Now, there is another way to do this. You can go on and shove the equations in each other. All right? G of f of x is equal to, all right, g is the square root of x plus 7. Now, everywhere you have an x, you're going to put in f. So this is x squared plus 2 plus 7, okay? You can do it this way, but this gets to be algebraically quite a bit of a mess. And then, of course, go take your limit. All right, pause the video. Now, the trig functions are very, very straightforward. The limit as x approaches c of sine of x is sine of c. The limit as x approaches c of tan x is tan of c. Now, some of these you have to make sure, of course, that the value is defined. We don't want to be taking 1 over 0. So the limit as x goes to 1 of cosine of pi x is just cosine of pi, or negative 1. Now, what do you do if a function agrees on all but one point? And we use this quite a bit. We get ourselves out of some messes with this theorem. If c is a real number and f of x equals g of x at all except one point in an open interval that contains c, then the limit as x approaches c for f of x is equal to, and is equal to the limit as x approaches c of g of x. So basically what we try to do is we try to pick a g that for which the limit exists and is the exact same as f at every point except 1. And we do that in, for example, this example right here. The limit as x goes to 3 blows this up. All right. So what I'm going to do is I'm going to cheat a little bit. I'm going to say this is a limit as x goes to 3, and I'm going to factor this out right here. And this is cheating, okay? That's what I call a cheat. All right. So if I let f of x equal x squared minus 3x divided by x minus 3, and g of x equal x. These are the same function except at x equals 3. Then the limit as x goes to 3 of f of x is equal to the limit as x goes to 3 of g of x, which is 3. This is how we handle getting rid of the point singularities in a denominator. You just do what you can do to factor it out. All right, your turn. Pause video. There are strategies for finding limits. Of course, the first one is recognize the easy ones that you can get by direct substitution. When you can't plug c in, because it's usually in the denominator, then find another function g that you can. And then you can apply analytically. You can apply theorem 1.7. Or you can always use graphs or tables. There's also something called a dividing out technique, which is basically what I've been kind of cheating and doing. All right, if I look at, I'm going to factor both of these. So this is x minus 2, x plus 2, x minus 1, divided by x minus 1, x plus 1. These go away. This becomes x plus 2 divided by x plus 1. Now when I take the limit, as x goes to 1 of this, I get 3 over 2, or 1.5.